Okay. Yeah, Honey is here. Yeah, she went to the bathroom and will be here. Okay. Will you go to that symposium? Not sure. Yeah, actually, I think that's a good opportunity. Yeah. Yeah, because like I want to write a paper, a conference paper for this final. Yeah, I talked about it with you, but I think yeah, but firstly we need yeah, I will talk about it with you like in a specific time. Yeah, let's start this class. Yeah, like in the chapter 3, do you remember what we are mainly focused on? What's the name for the chapter 3? Fourier series. Yeah, Fourier series, like representation, I'm right? Yeah, and today we will talk about chapter 4, and the chapter 4 will focus on Fourier transform. Yeah, and let me ask you a question. The Fourier series focus on what kind of signal? A lot of signals, yeah. But all those signals are periodic. Yeah, we talk about that. All the signals, if you want to do a FS representation, those signals must be a periodic signal. But how about the non-periodic signal? We need tools to analyze that, am I right? So that's the reason why we want to learn Fourier transform. The Fourier transform is specific for non-periodic signal. Yeah, let's start. Okay, yeah, today's goal, we will try to define the continuous time Fourier transform for signals and the impulse response of the LIT system. And then we will try to discuss the magnitude and the phase spectrum of the FT. Yeah, the FS, Fourier series, we short name is FS. The Fourier transform, we short it is FT. Yeah, and then we try to compute the FT, like a non-periodic signal. A periodic, it means a non-periodic signal. Okay, let's try, before we talk about the Fourier transform, let's talk about the class rule map. Do you remember what's in the beginning of this class, what we are focused on? Do you remember? What's the name for the chapter 1? System and signals. Yeah, just some like fundamental thing. Yeah, just talk about what is signal, what is fundamental, what is like a system, and what's the properties for those one, and what kind of what type of the signals. Yeah, so we talk about the DT, CT signal systems. Yeah, basic signals, LIT systems, convolution thing. I'm right. And then we talk about the Fourier, like a Fourier series, like actually it focuses on CT periodic signals. We will talk about that. And then today, from the chapter 4, we focus on the continuous time Fourier transform, like a like this two, this one, focus on the non-periodic signals or impulse response. Yeah, and then after we finish the Fourier transform, actually the Fourier series and the Fourier transform can help us to understand the sampling. Yeah, why we can use sampling to analyze the signal, and then why the modulation and the multiplexing, like communication. How can we, like your phone and the computer always communicate with other phone, with other computer, am I right? Yeah, how? Like our computer actually is an isolated thing, am I right? How can you upload your data, yeah, to other to the server, to the other to communicate with other devices? Yeah, actually, the signal that system is very important for that part. Yeah, and I don't know if we have time for for these applications. Yeah, but we will try to. I will try to give you a summary. Summarize if we don't have enough time for like a detailedly to talk about that. I will give you some like general ideas for that. Yeah. Okay. Let's talk about the FT, like a Fourier transform. Yeah. For the FS synthetic and like analysis, we have those two equations. You remember that, right? One is for synthesis, and the other is for analysis. The synthesis is just like try to represent the signal in a frequency domain, like a form. That makes sense. Because you can see this one is just a magnitude. This is just like the phase, right? The frequency and the magnitude. And then this is just the coefficient for Fs coefficient for the for this in this equation. That makes sense to you? Yeah. So this is Fs like synthesis and analysis. And let's talk about Ft. You will find it's very similar. Yeah. We spend a lot of time on Fs representation. For the Ft, you will find it's very similar. Yeah. The Ft provides a linear combination of complex exponentials in the form of an integral for non-periodic signal representation, or the system frequency response from impulse response. Yeah, which means the Ft is just like a specific for the non-periodic signal, and the system response from impulse response. Yeah, like this is the Fourier transform due. Yeah, and then you will see the Fourier also for the Fourier transform. There are two different equations, very important different equations. One is Ft synthesis equation. You can see like one signal can be represented in the magnitude and the like a phase, right? Frequency. Like this is just some frequency, right? Yeah, this is just like how to represent a signal using the in a frequency domain. Yeah, and then this is Ft synthesis, and the other is yeah, you can see compare with this one and this one. Did you notice the do you notice the difference? You can see it's very similar, am I right? Yeah. The difference is this is like summation, and this is the integral. Do you know when we'll use summation? When we'll use integral? Do you know? You can see two are like something, am I right? Like add something together. So when you use the summation, when you use the integral, do you know? Huh? Specific what? Specific. Uh-huh. Yeah, I think maybe you just point out the maybe the definition general thing, am I right? But let me tell you the most important difference. If you observe very carefully, the summation always used when the atom is not limited, like is limited, it's not infinite. Yeah, or you just talk about that, right? You can see you add something. It's from negative infinity to positive infinity, but the number will be limited. It's not infinite, but the integral, which means the number will limited. Yeah, the number is unlimited. It's infinite. Yeah. Do you know why? Yeah, we know like you remember there is a very important statement, like all the periodic signal can be generated from a series of like a sinusoidal signal. Am I right? You know that, am I right? We talk about that all the periodic can be like generated from different like sinusoidal signal. You can see for the periodic signal, actually you can find the specific sinusoidal signal. Am I right? And this sinusoidal signal is like there is no there is a limited number. Yeah, which means for if you represent a signal in a flux domain, you will find out one kilohertz, like 2 kilohertz, 10 kilohertz. It will combine with those three, but it will limit it. But for the non-periodic signal, what does that mean? Which means that you try to find all the like frequency like you try to find all the frequency, yeah, because you can see all the signal actually you can represent it in some specific frequency. But for the non-periodic, it's unlimited frequency. You don't know, like you are not sure which one is involved in this signal, am I right? You just try to try to go through all the frequency and to see if it is involved or not involved in this signal. Yeah, so that's the reason why because non-periodic, which means you cannot find the specific sinusoidal signals. Yeah, maybe the signal may be generated by unlimited sinusoidal signal. That makes sense to you? Yeah, that's the reason why this is an integral. And then this one, x, g, omega, actually, you can see this is a function, right? It's related to omega. What's omega? What's omega? Actually, it's frequency. That makes sense to you? Yeah, when we talk about that, it's angular frequency, right? So which means your for the non-periodic, your ft coefficient is related to your frequency. And this one is just similar, yeah, like with this one. Yeah, but this one is also related to your frequency, right? There is no k because it doesn't involve just a harmonic signal. Yeah, this is for the non-periodic signal. And also, the difference is the integral, the summation changed to integral, and the k omega naught changed to omega. Yeah, and the x, the ak changed to x g omega. Yeah, those three very important change. And then we also can have ft analysis equation. Yeah, similar with fs analysis equation. It's just how to calculate the coefficient. Yeah, am I right? Yeah, this one is fs coefficient. This is just ft coefficient, and the equation is very similar. Yeah, but you can see here it's just one period, right? So for non-period signal, what's a period? Yeah, this is a tricky one. Actually, I think I asked these questions for non-periodic signal. What's periodic? What's a period? Sorry, what's a period? Yeah, you can see for periodic signal, you can find the period on this. For the non-periodic signal, which means you can consider the whole signal as a one period, right? So which means your duration should be from negative infinity to the positive infinity. That makes sense to you? Yeah, and the similar thing, this is just the signal, and this is just this part. But here is also negative here. Does it make sense to you? Yeah, actually you compare the FT synthesis and the FS synthesis. It's very similar, just a change something because it's non-periodic. That makes sense to you? Yeah, any questions so far? Yeah, okay. Then let's talk about the FT, coefficient. Yeah, you can see for the FT coefficient, for the FS coefficient, AK, we know it includes two different information. One is what? AK also includes two different information. You know what's that? One is amplitude, am I right? Yeah, magnitude, amplitude. Yeah. The other is phase, am I right? Yeah, actually for the FT coefficient, it also includes two different information, the magnitude and the phase. Yeah. And then actually you can see for the FT coefficient, we can represent just using this equation. Now equation using this form. Does it make sense to you? Because for the FT coefficient, it must be a complex number. Yeah, a complex value, and then real part plus the imaginary part. It's that value. That makes sense to you? Yeah, and then let's try to talk about the magnitude. For a complex number, what's magnitude for the complex number? Do you know? Yeah, actually there is a equation to calculate the amplitude or magnitude for the complex number. I think if I this one, I think you must have seen this before. Yeah, if you have A plus BG, and then you to calculate the magnitude, that's A, B. Am I right? Yeah, you learned that before. Yeah, the magnitude for the FT coefficient. And then let's talk about we call it magnitude spectrum. And this is just a power distribution over all frequencies. Why all frequencies? Do you remember? I just talked about that. Do you know why all frequencies? Do you know? Do you know? Yeah, like a power distribution over all frequencies. Do you know why? You can see this omega is just like from infinity to the negative infinity to the positive infinity. Because this signal is non-periodic. You don't know where is the specific frequency, what's the specific frequency involved in this signal. So this power is just distributed over all frequencies. Yeah. Okay, and let's talk about the magnitude. Yeah, let's talk about the freeze. For the freeze, also we have the equation, the angle equal this one E divided A. Yeah, you also have this equation. I think you learned this equation before. Yeah, you can see the FT coefficient is very similar with the FS coefficient. Yeah, that makes sense. It includes two different information. One is magnitude, the other is freeze. Yeah, any question so far? Okay, yeah, this freeze shift, it's all related to shift the different frequencies. Yeah, okay, and then you can see, actually, you can also represent your FT coefficient using this equation. Yeah, because it includes two different parts, the magnitude and the freeze. Yeah, very similar with the FS coefficient. That makes sense to you? Yeah, any questions so far? Yeah, if you understand, totally understand the FS, representation, FS synthesis, FS analysis, FS coefficient, actually the FT is very easy for you to understand because it's very similar. Yeah, any questions so far? Okay, and then let's talk about, you can see, if you try to draw the magnitude, you will find the magnitude is just similar like this. And then the freeze is just similar like this. Yeah, and then the question is, what is the freeze spectrum of a real FT function? Real FT function, which means that this is a real signal. Yeah, it's not like the real non-periodic signal. Yeah, do you know what is a freeze spectrum? Like this one? For the real signal. Do you know what's the phase shift? Yeah, actually you can see, you can tell from here what is a freeze spectrum. This is just a freeze spectrum, and this is just a FT, like a coefficient for the real signal. And what is this function? Actually, it's an odd function. That makes sense to you? Yeah, this one is an odd function. And for the magnitude, it's an even function. Yeah, that makes sense to you? Yeah, any questions so far? Okay, and then let's talk about the frequency response for different filter. Yeah, you can see in many classes, you learn many filters. Am I right? Have you ever, can you give me some examples? Yeah, I know like you must learn some filters in some classes. Give me some examples. Can you? Huh? Yeah, high pass filter, low pass filter. Yeah, actually, you know, like the high pass filter, low pass filter, what does that mean? Huh? Low pass filter, what does that mean? Can you speak it? Yeah, low pass filter, which means pass the low what? What? Signal, am I right? Low water signal. Yeah, like you just pass some signal, am I right? This signal has some low what? Huh? Just remember, all the filter, not all, yeah. When you talk about the low pass filter and high pass filter, it specifically mention the frequency. Yeah, which means if you have the low pass filter, which means you just pass the low frequency signal. This system just pass the low frequency signal, and the high frequency it will stop like that. And the high pass filter, which means your filter just pass the high frequency signal, and the low frequency will stop. Yeah, when you talk about the filters, it always related to the frequency. Yeah, just remember that. Almost, yeah. And then let's talk about like the frequency response for different filters. You can see usually what like let me give you an example. Yeah, for example, yeah, you have a signal. For example, the voltage signal. Am I right? For your voltage signal, if you this is zero, am I right? This is for example, this is T. This is your voltage. What's like a domain for this signal? Actually, this is time domain, am I right? Which means in the zero like a 0 second 0 time you give the system a power and it is 2 volt. For example, it's 2 volt, am I right? And then you will find if it is an annual like a system and your voltage is always 2 volt, am I right? Yeah, but this is just a DC voltage. But if your like the voltage is the AC, which means you have your power has a frequency. Am I right? Yeah, but you know, like for many complicated signal, it doesn't have only one frequency. Am I right? This is the frequency. This is your like a signal like XT, which means your signal have like for example 20 hertz. This is like 1 gigahertz and the 2 gigahertz. Am I right? And your signal include those three different frequencies. Am I right? Yeah, this is just the Brooks domain signal, Brooks domain representation. Am I right? If you want low pass filter, what does that mean? Pass the low frequency, am I right? Which means I just want to get the low frequency signal. I don't want to get this one. Then you need to remove this one, am I right? Try to remove. What does that mean? Which means you multiple zero here, multiple zero here, and then you just remove this one and get this one, multiple one here, am I right? That makes sense to you? And then if you have a band pass filter, which means you just want this one, you don't want this one, you don't want this one, which means you multiple zero here, multiple zero here, multiple one here. And the high pass filter is similarly multiple one here. I got this one, multiple zero. That makes sense to you? Yeah. And then let's talk about this one. You can see this is just that like a coefficient. Yeah, this one is just that coefficient. You want to like a multiple. Yeah, you can see this one is just try to if you just this one also we know like it can be represented this one is just like the ft coefficient, am I right? It can be represented in magnitude and the phase, am I right? And then you can see if your like if your like coefficient is just in this area, what does that mean? Which means you can see here, your signal is just the coefficient multiple the like a specific frequency, am I right? Which means if your like coefficient in this range and the other range is just 0, what does that mean? What does that mean? Yeah, this is 0, which means this is omega, like frequency. Look at me. Yeah, this is the frequency, am I right? This is 0, and this area, what does that mean? Which means this is quite low frequency, am I right? And if you have this coefficient for your like frequency, which means for the high frequency there is 0, am I right? But for the low frequency you have some value. What does that mean? Which means this one is what? Is a what? Low frequency filter. That makes sense to you? Yeah, because you can see only the low frequency has a value, has a coefficient. That makes sense to you? Any question? Yeah. How about this one? How about this one? It's also low frequency, yeah, because lower than this one. That makes sense to you? Yeah, any question? Any question? How about this one? Not very high, but you can see it's quite a band filtering, which means I just try to get those two. Others I don't want. That makes sense to you? Huh? Oh yeah, doesn't matter because you can see here it's just a 0. That makes sense to you? Yeah, yeah. Then you try to understand like the low filtering and high pass, low pass filtering and high pass filter. Actually, the filtering is very common idea in many classes. You almost can see all these ideas in almost every like engineering class. Yeah, so you just remember it always talk about the frequency. Yeah, and then you can see this is a low pass filter. Yeah, sorry. Also, yeah, because this is just frequency, which means this is 0. I just focus on this low frequency. And yeah, also this one, because this is lower. And this one is just, I try to like bend this, get those two. Okay, band pass filter. Yeah. You can see, usually when we talk about the like a filter, we just focus on 0 to like a positive infinity. We usually didn't focus on this part. Yeah, the negative part. Yeah, just like this is just a common idea for that. Okay, and you can see here. Yeah, this is just like a low pass filter. Yeah, when we talk about the filtering, you usually see this diagrams, am I right? Yeah, this is the low pass filter because you only have the coefficient for this part, am I right? Yeah, just understand, just try to understand this one is just this part, the coefficient, which means here for this frequency you have the coefficient. For the high frequency, you don't have the coefficient, which means the coefficient will be 0. Am I right? Which means the high frequency will be removed. That makes sense to you? Any question? Yeah. And you can see this is low pass and this is high pass because the low part is 0. Only the high pass, frequency has a value. High frequency coefficient has a value. That makes sense to you? Yeah, and then this is a band pass filtering, and this is band stop. Band stop, which means only this will be 0. I don't have this part. That makes sense to you? Any questions so far? Okay, that's great. And let's try to talk about one example. You can see, actually, the filtering is very useful for many areas. This is just for the like image processing. You can see this image image is just like a have some like very unclear. It's very unclear. Yeah, but you can apply the low pass filter and to remove the noise. Yeah, which means that you only save the low frequency signal, but remove the high frequency signal because I don't know if I talk about this. Almost all the noise is high frequency signal. Yeah, you can see after you apply a low pass filter, you have this result. This result is quite better. Yeah, it's better than the previous one. Yeah, this is just like a filter, like a application. Yeah, for similar like this. Yeah, you have this is your original one, and then you want to get the sharp image. We know like the sharp details is just related to the high frequency signal. Yeah, so we want to do what? We want to keep the high frequency part. We want to remove the low frequency part. Am I right? So then we apply a high pass filtering, and then get this sharp image. That makes sense to you? Yeah, actually, this is just for image processing. Actually, many areas use the high pass filtering, low pass filtering, but it's a similar idea. Yeah. Any questions so far? Okay, and then the other example, you can see this is a video. Yeah, this is a video. Actually, if you see the video, this video is just a play by the time, am I right? Actually, if you learn some images, yeah, you will. If you take my computer vision, maybe you will understand this more. Yeah, but you can see for the video, it's a time domain signal. Am I right? It will play as a time pass. Am I right? I play this video, then you will find out as a time pass. You see this video. Am I right? But this one also is this signal, this video signal. This one is just the frequency domain signal. Amazing, I'm right? Yeah, in the frequency, it's just similar like that. Yeah, because you can see all like for this video, the frequency, this is just the normal frequency. Yeah, all the signals is almost like in this area. Am I right? But you can see there are those two change line. Did you notice that? Yeah, actually, those two different line is noise. You can see for the original video, it's not very clear. Am I right? Actually, those two lines is noise. Yeah, and then we want to, if we want, obvious we want to a clear video. Am I right? Then what we will do? We will try to remove this frequency signal. Am I right? Yeah, because those are like a noise. Am I right? What we will do? We will try to create this bond. This like a black like a black in video black signals in frequency domain and try to cover those two like area because after you cover it, it will become black. And then you just try to multiply this one with the frequency domain signal, and then you cover those two lines, and then you can see after you cover it, it just become this one, and then if you get the time domain signal, it will become this one. Amazing, am I right? Yeah, am I clear? Yeah, because you can see this is just the frequency domain to represent this signal. And you will find that there are some noise. You want to try to remove this noise, and then you created this function in frequency domain and try to cover those two. And after you cover it, you get this one. And then you will find that if you just transfer your frequency domain signal to the time domain signal, and then you will get this one. Yeah, amazing, right? Yeah. So that's the reason why the signal and system is very important. Yeah, because it's a fundamental like a class for many like advanced classes. Yeah. Any questions so far? Okay. And then let's try to review one. Actually, yeah. for the computer vision, actually, like NASA 4, we have that one, and those students, most of them don't have the signals and the system. Yeah, but I try to avoid that part. Actually, for the computer vision, there are many topics related to frequency domain, but I just try to avoid that part. Yeah, just a little topic related to the frequency domain. Yeah, don't be afraid that. Yeah. Mm,
But we're calling it definitely now, so it's fine, but like, if someone hasn't taken this class, wouldn't take that class, they should take this class first.
Yeah, I strongly suggest you to take this class, but if you didn't, that's fine. Yeah, I will try to yeah, don't worry about that. Yeah. Any other questions? Okay. And then let's talk about some examples. Okay, you can see this is the signal. And then let's try to get the FT coefficient. Yeah, you can see this is the equation for the FT coefficient. Am I right? Let's review some examples. Yeah, and then this one. Do you know? Yeah, this one is just what we talk about here. This is just FT. This FT analysis equation. Am I right? And then yeah, this is just you just try to calculate the FT coefficient using this equation, and then put this xt here, and you will get this one. That makes sense? And what's the next step? Actually, we learned this before. What's the next step? What's the next step? Yeah, try to remove what? UT, am I right? Yeah, because, yeah, I think we talked about this in chapter 2. Yeah, because you can see the UT is we just try to remove the UT, and then the equation will be easier for us to analyze. Yeah. How to remove the UT? Do you know? What is UT? Firstly, unit step function. Am I right? Unit step function. What does it mean? Which means UT equal 1 when t greater equal 0. Otherwise, that makes sense. Yeah. So which means here t is from negative infinity to the positive infinity. When you remove ut, which means it's just from 0 to positive, and then you can remove that one. That makes sense. And then those two parts left, and you just try to change from convert this one to this one. I think this is easier for you to understand. And then, yeah, this one is easy for us to calculation. You got this one, and then yeah, you got this one. This is your FT coefficient. Am I right? And for the FT coefficient, we know it includes two different parts. One is magnitude. Yeah, this one is also equal to this one. It's a similar thing. It's the same thing. Yeah, and then it equal this one. And we know the magnitude you can calculate in this equation, and the phase you can calculate in this equation. And then let's calculate it. It's equal to this one, and it's equal to this one. And if you draw the magnitude, you will find this equation. Yeah, you can see for the real signal and the magnitude will be even. That makes sense to you? Any questions so far? Okay, let's check the other one. This one. Actually, did you notice the difference between this one and this one? This one and this one? Yeah. Only here is a negative AT. Here is AT. Here is negative UT. Here is U negative T. Yeah, it's very similar. Am I right? So let's talk about use the same equation. Am I right? And then put the xt inside the into the equation. And then what's the next step? Yeah, remove the ut. And then u negative t. What does that mean? Which means u negative t. Which means negative t greater or equal than 0 will be 1, right? Which means t is smaller equal than 0 will be 1. All right? Yeah, which means you will have this. That makes sense to you? Yeah, and then, yeah, similar with the previous one, you will find this one, you can get it like this, and then use this equation, and then similar like that. And if you calculate the magnitude and the freeze, you'll find, you can get this one. Let's compare this one and this one. You can see the magnitude is the same thing. The freeze is just like here is the previous is there is a negative, there is no negative. Yeah, that makes sense to you? Yeah, and then let's talk about the other one. Yeah, this one, E, negative A, absolute T. And this one, like if you draw like a diagram, draw the diagram, you will find that this is xt. And then this one equal this one. I'm right? Do you know why? Actually, we talked about this before. Yeah, which means when t greater or equal than 0, this one will equal this one. I'm right? And when t smaller equal than smaller 0, and then you will have this one. That makes sense to you? And this part is just give you t greater equal than 0. This is just t smaller than 0. That makes sense to you? And then similar, you can see similar with the previous two. And then you will find the x like the ft coefficient will equal this one. And then you okay, what kind of function is x g? Like what kind of function is ft coefficient? You can see it is a real signal. It's a real function, real signal. That makes sense to you? There is no g, am I right? Yeah, and then actually, yeah, this one is a real and even signal. Am I right? Yeah, actually, we know like if you for the fs series, if your fs coefficient is real and even, your signal is real and even. So for the ft coefficient, does it have the same conclusion? What do you think? Yeah, we know like for the fs series, yeah, we have the symmetric property, am I right? For the symmetric property, we know like if your fs coefficient is real and even, your signal is real and even. And for the ft, if you have the real even ft, is the signal real and even? Yes. Yes, you can try to improve that. Yeah, actually, it's very similar with FT, like FS coefficient. We will learn some properties. It's very similar. Okay, and then those three, it's just this one, and this one. This one. Yeah, actually, those three is very important for us to calculate the FT coefficient. Similar with that two often used FS pairs. Yeah, we will like use those three, like a common used FT, like FT pairs, and then use some properties to calculate the like some signals FT coefficient. Yeah, does this make sense to you? Okay, and we will continue next time. Focus on the FT coefficient, and FT like synthesis and analysis. Any questions so far? Okay.